Activity 4, we're going to talk about compound events. I'm going to fly through the first example. We're just going to kind of get our brains warmed up with it, and then I'm going to move to the second one. It's really not a big deal to do this compound event. This video probably won't even take us the whole period. Yes. So here we go. This is our review. So you've got a juice company, and for the juice you get to pick a fruit and a vegetable. How many different events do we have, or how many, like what I call selections, holes? How many things do we have to pick if in each juice you get a fruit and a vegetable? How many holes do we have to fill? 2. We have a fruit choice and we have a vegetable choice. How many different things can fill my first hole? 4. How many things can fill my second hole?
5.
And so how many different options do I have total? 4 times 5 is 20 different options that can be made, or combinations of different juices. With me. Okay? So boom, this is our tree diagram. Yes, again, we talked about it. Should you know how to make a tree diagram? Yes. Should you know how to do a organized list? Yes. Now, does the action of choosing a fruit affect the outcome of choosing a vegetable flavor? For you personally, maybe. But for the purpose of these juice makers, will they have every different combination possible with this? Is there anything that's limiting the other one? No. That sounds awesome. Alright, so it does not affect the flavor, so we're going to skip this. Alright. That should have warmed us up. So we're skipping a lot of that. Alright. We are on flipping a coin. Did we pass the word? Did we pass the compound?
Yes.
What page is that on? Page mine. Alright, this is the thing you need to know. A compound event is an event that consists of 2 or more events. Compound event is an event that consists of 2 or more events. It means you have event 1, you got event 2, and we're seeing when those happen. Now, there's 2 different ways. There's 2 different ways that this can happen. One can be with and one we're going to talk about can be with or. Today we're going to focus on the and. Now think about this. I'm trying to think how to phrase this. Which one's going to have higher chances of happening? Ands or ors? A lot of people think ands, but it's actually ors. Think about my logic, ready? Let's say I'm making a group of students. And I say, I want people to come stand up here who are blonde hair and blue eye. How many criteria do you have to fit in order to get into my group? 2. What if I said, okay, I want the people who are blonde hair or blue eye? How many the criteria do you have to fit to get into my group? Just one of them. Now, one of the things that you have to be careful with ors is they might have some overlapping parts. Are you with me on that? Like, you're going to, so we'll get there eventually, but you're going to have blonde-haired people, right? You're going to have blue-eyed people, but you're going to have blonde hair and you can't count them for both groups. Do you get what I'm saying? We'll get there later on. That's one of the tricky parts of or. So again, I just like to preview some of the stuff. But today we're really focusing on and is pretty darn easy. For and, all you do is you find the probability of the first event, and you times it by the probability of the second event happening. So if I say, what's the probability of A and B happening? You find the probability of A, you find the probability of B, and you multiply those 2 events together. And you will get the probability of them both happening at the same time. Okay? you talking about today?
So, a compound event is is it basically anything that has more than one outcome?
Two or more events happening. All these that I've given you is compound events.
Yeah, we've only done compound
It can
events,
be
right?
and, it can be or. We haven't done any events yet, really. We haven't really done a lot of probability. We're now starting to get into what's the chances of this happening. We haven't really done a lot of those problems. We talked about how many outcomes there are. We talked about counting principle, but we haven't done anything with it yet. Today, yes.
You said that you got blonde hair. It's blonde hair.
No. They would be up there, but you can only count them in one of the groups. You can pick. We'll get to that later on. But you can't count them twice. You can't count them for blonde hair and count them for blue eyes because your number's going to be inflated then because you're going to say, we have 14 people that are supposed to meet this, and there's only 10 people up here. Does that make sense? We'll get to that or later on. Matt, do you have a question?
I was going to say that this is related to inequalities because I do remember hearing about N and Or's inequalities.
That's for X. X being like, X acts kind of like that because if I say and for X, it has to satisfy both things. So like if I say X has to be greater than 3 and less than 5, right?
Yeah.
It's the numbers in between 3 and 5 only.
Yeah.
Because it's got to be bigger than 3, less than 5. So it's got to be this is my domain of my X's.
Okay.
Where if I say X can be less than 3 or greater than 5, then I've got from here less than and all of these numbers I will satisfy this number and all the way over here. So it's, you get what I mean by that?
Yeah.
So that's how it kind of has to do with it.
Okay.
Alright, so what's the probability of, so you flip 3 coins and record the results of each flip. What's the probability that all 3 coins land heads up? How do we find the compound? What do we find? The probability of the first event, probability of second, probability of third, multiply them all together. What's the probability of the first one landing heads up?
50.
1 half. We write it as a fraction. 1 out of 2, right? What's the desired outcome? Heads. How many of them are on a coin? 1. How many different total things are there on a coin? 2. 1 out of 2, right? Times, what's the chances of the second one happening? What's the chance of the third one happening?
1/2.
What's the chance of that totally happening? 1/8. Multiply them. Multiply them. You with me on that? How do we multiply fractions? Top times tops and bottom times bottom. Alright, what's the probability that the first 2 coins lands head up and the third coin lands tails up? What's the probability of the first event happening? Half. What's the probability of the second event happening? Half. What's the probability of the third one happening? Half. So this one is also, the probability of that happening is still 1/8. With me on this. What's the probability that the second coin lands tails up? How many events are still happening in this problem? How many events are still happening in this problem? How many coins am I flipping? 3. Do I care about the first event? No. Do I care about the third event? No. What's the only event I care about? And what's the second event I want to happen? Tails up. What's the probability of that happening?
1/2.
So what's the probability of this coming true? 1/2. Because the first one I flip is either going to be what? You flip a coin, and it lands on what?
Heads or tails.
And if you guys would have said, like, I was hoping you'd go, lands on heads, I'd be like, correct. heads or tails. The third event is going to be heads or tails. It doesn't matter. This does not limit the first or second or the third. It wants the second one to land tails up. The event of that happening is 1/2. What is the probability of flipping heads on the first coin and tails on the third? What are the only two events that are really affecting this? First and third. What's the probability of the first one landing heads up? Tails? 1/2 times 1/2 is 1/4. Does that make sense?
It kind of doesn't like mention the same point though.
It does. It right up here. But it's starting to get to where the second coin doesn't matter because its probability of you flipping it is 1.
Yeah.
So what's 1 times any number?
1.
So,
I mean, it's.
So when I multiply, so if right here, I could have done 1/2 times 1 times 1/2 because the second coin doesn't affect the probability. It doesn't tell me it has to be heads or tails.
So there's a little bit of inferring there.
Yes, well, I'm reading it and they're saying what's the probability of the first coin and the tails on the third coin. They don't tell me. Basically, that means my second coin can be
1.
heads or tails. It doesn't matter. So it's not going to affect my probability.
Okay.
copy card.
Good one. All right. Like Derek does the ridiculousness of this problem.
Please no.
Suppose you flip a coin 50 times. What's the probability of flipping? The first and second coins will land on heads. Okay? Derek does this and acts like he's going to flip this coin 50 times. By the way, if you were saying they all land on heads, right, it would be a 1/2 times 1/2 times 1/2 to the 50th power. You realize how small that chance would be? Okay? What he does is ridiculous. What is the only coin that we care about? Do we care that you're going to flip 50 coins? What are the only two that we care about? And we want them to be heads. What's the chance of the first event happening?
1/2.
What's the chance of the second one? So what's the chance that when you flip 50 coins, the first and second coins are both heads? 1/4. Does that make sense? I have no idea. Derek is extra. Alright, we already did this, but this is what it's called. Rule of compound probability involving what? Because we've already discussed that we're going to have a rule of compound probability involving OR. So this is the AND rule. Does that make sense? You're going to need to know this for the OR rule, by the way. We use the AND rule for the OR rule. That's why we teach it first. Right? So here we go. This problem, some of this problem I'm going, really? This is stupid. I wish they would have done this as marbles.
Yeah, that makes a little bit more sense.
For socks, this is stupid. Well, this is how my son's drawer is. And this is literally how he picks his sock. Like I said, this is my first period. He has a beige church sock on. So imagine that's like the mid-calf kind of level sock. Kind of like a silkier sock. And a transformer sock. That is an ankle sock. Completely black with Optimus Prime. He has shorts on. He doesn't care. No. Alright, so definitely a Kai. Now, I don't get this part, and we don't have to. We just, this is what they're telling us. It doesn't make sense. I agree with you. You've got a person, you are reaching in here like a crane. You're not looking. So you're doing like the crane game. Picking out a sock, seeing what you got. You are choosing a sock, and you all, for some reason, replace it and pick another sock. So you're going to pick 2 socks, but you're not going to keep 2 socks. I don't know what situation this is used for, but you have chosen 2 socks. Do you understand? Now, why is it important that you replace the sock?
Is that
Does it change the odds if you replace it? Or let's not do odds, let's do probability. Because remember, does it change your chances?
that changes the total possible outcome?
If you replace it, does
Oh,
it change it?
oh.
No, it's the same as you did before. So these are two independent events. They don't affect each other because the same chances are when I pull the first one as I pull the second one because of that replacement. Now, how would we really choose socks? Is you would reach in there, and I do this all the time. Close my eyes, just grab, and
Why? Like, what's
just
the
kidding.
okay.
So you grab one, you would keep that one sock, so that means you would not replace it. You would grab a second sock, so now those two events are now becoming dependent on each other. It changes my probability and my chances of the second event happening. Total different question. We are going to do that in just a minute. For this one, we are replacing. You with me? Alright, so here we go. Alright. We all should know how to do the tree diagrams, blah, blah, blah. We should know, okay, how many different events do I have that I need to take care of? How many holes do I have? How many situations I got to take care of? Two. How many different possibilities do I have for my first one? Six. How many possibilities for my second event? Six. Why? Because I'm replacing. So I still have six, and I still have six, and 6 times 6 is 36 different outcomes.
A lot of possibilities for socks.
Right? So here we go. What is the probability of choosing a blue sock and then a red sock? So what's the probability of choosing a blue sock?
6.
Do you see how they got that? What's the probability of choosing a red sock?
3rd.
It's 2 out of 6, which reduces to 1/3. And before I would multiply them, I would reduce them because the smaller the numbers, the easier it is to reduce. You with me? And then when I multiply 1/6 times 1/3, I get 1/18. That's the chances of that event happening. What you think? You with me on it?
Pretty cool.
Okay? A red sock, and then a sock that is not blue. So let's just attack the red sock. We already know that there's a 1/3 chance of pulling a red sock, correct? With me? How do we find the chances of not pulling a blue? Now for this problem, you could just count the other two, like you could just add them up. But what if I had 1,000 different yellows, blues, orange, greens, purples, pinks, fuchsias, magenta, right? And I say not purple, not pink, but I have thousands of other colors. Do I want to sit there and take the time and add all those colors up? What did we say we could do instead? Subtract the knots from the total, and that will be the remainings that are not those two. Are you with me? So for this one, how many are blue? 1. How many does that mean are not blue? 5. Do you get how we did that? So what they do here is they show a 1, which is just the total is always, 1, minus what's the probability of pulling a blue? 1/6. What's that mean the probability of not pulling a blue is 5/6. Then I would multiply the 1/3 times the 5/6. And again, the reason that this is, you guys are going, why even learn that? Because like I said, in this example, it's easy because the numbers are small. When you start getting into the thousands or millions or something like that, which you think there are people who deal with those kinds of numbers when they're talking probability. Well, I wanted to talk about this. I need to remember. We'll talk about it. Remind me to talk about the NCAA tournament. Brackets. The chances, did you know that someone put out, I think, was it 1 million or million. A couple of years ago, Warren Buffett, I think, said if you get a perfect bracket, he would give you either $1 million or $1 billion. There's 64 teams who start the tournament. There's no way there's an incorrect. I don't think so. It's true. The reason I'm saying that is because. Alright, so 2 socks, the first one being green. Now with this one, 2 socks, you're picking 2 socks. The first one being green. What is the only one that is affecting your outcome? The first one. What can the second one be? Any color. So do you understand why it's a 6 out of 6? So really it's just the only first event is the only one that you're really worried about. Now let's go quickly. If we had this next one, it's going to be not replacing it. So that's how they're going to change this problem. What's the probability of pulling a blue sock? 1 out of 6. What's the probability of a red sock? Now notice it's 2 out of 5 because now I've pulled this blue sock. You always assume the first one is true. So when I go to look at my leftovers, there's now a blue sock that's gone. Are you with me? You always assume the first one happens. So like, if I said, what's the probability of pulling 2 red socks? How many red socks are there total in this thing? 2. So it would be 2 out of 6 times. Now what would be my next probability?
Wait, what?
1 out of 5. I did not replace it. Listen, I did not replace it. So it's 2 out of 6 because there's 2 red socks, 6 total. When I pull my first sock, I assume that I pulled a what color? A red one, and so I now don't have 2 reds in there anymore. I only have 1 red. How many socks are there total now? 5. So I have 1 out of 5 for that second event to happen. And so I've multiplied 2 6 times 1/5 to get my chances of that event happening together, the compound. And, are you with me? Always assume the first one is true. So when you pull a red sock, you go, oh wow, I got a red sock. And you go, okay, what's the chances of the second event happening? Multiply those together. That's the chance that them both happen. What? Yes, that's how I just screen game. Alright. I think we're good. Any questions on that? Make sense? Alright. Alright, so problem 4, this is definitely where it gets a little bit more dicey, but we can think through this. So 2 red socks, 1 blue sock, 3 green socks are in a drawer. 1 sock is randomly chosen without replacing. And in the drawer, and the second sock is randomly chosen. What's the probability that the second sock is red? Alright. So we want the second sock to be red, but the first sock can be red or not red. The desired outcomes are red in red or not red in red. So that means that you can have your first sock being red and your second sock being red, and it meets the criteria because all we care about is the second sock being red. In this case, is my second sock red? Yes. But in this one, we can do not red happening, and then right here, again, as long as this second sock is red, then I'm good. So here's what he did. He calculates the probability of choosing a red sock and a red sock. He counts the probability of a not red sock and a red sock, and then you add those 2 together. So what's the probability of a red sock being pulled? 2 out of 6. Well, what's the probability of the second one being red also? Is 1 out of 5. Because once I pull the first sock, I've pulled a red out. That means now instead of having 2 reds left, I only have 1 left red in there. Instead of being 6 socks, I didn't replace it, so there's only 5 socks. When I multiply that together, I get 2 30s. What's the probability of not a red? Well, there's 2 that are red, so that means that there's 4 that are not red. So 4 out of 6 is the probability of pulling a not red for the first sock. Pulling a red for the second one. Well, when I pull this one, I assume that I pull not a red, so that means I pull a green or a blue sock. So that means that there are still 2 socks in there that are red, and now out of 5 total, because one of those other socks is gone, so now I got 2/5 chance. When I multiply that together, I get 8 over 30. I add those together, and I get 10 over 30. And when I reduce that, I get a 1/3 chance of the second sock being red. Hope that makes sense. That's a very good problem. All right, Faith just makes an organized list and counts all the ones that are red second. So this one's no good because my red is first. This one is good because my red is second, red is second, red is second, 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 second. Sorry about that. So all these ones that have the R second are the ones she counted. When she counts that, she gets 10 out of a total of 30. Now we know that it's 30 because for my first slot I have 6 different choices. For the second one I have 5. 6 times 5 is 30, which makes sense for this organized list. Alright. 2 red socks, 1 blue, 3 green. 1 sock is randomly chosen without replacing it. Remember, that's huge. The second sock is chosen randomly. Then we want, what is the probability of the second sock being blue? So what I do is I like John's method. I would say, okay, what's the probability of pulling a blue and a blue? What's the probability of not pulling a blue and a blue? The only thing I care about is my second sock is blue. Well, if I pull a blue for the first one, I've got a 1 out of 6 chance of getting it. When I go to pull the second one right here, so pulling a blue first and a blue second, the probability of that happening is 0 because there's only 1 blue sock. So when I pull the first sock out, I got a 1 out of 6 chance. I assume I pull the blue one. How many blues are left if I pull the one that's out? There's none. So you have a 0 out of 5 of pull blue for the second one, and when I multiply that, I get 0. There's no chance of pulling a blue first and a blue second. So what's the chance of me pulling not a blue first? 5 out of 6. And then pulling a blue second? 1 out of 5, because I assume I pulled one of the other socks that's not blue. And there's now not 5 or 6 socks, so that's 5. And when I multiply that, I get 1 6. And then I add those two together, and 0 plus 1 6 is 1 6. You can check it with this, and you still get 1, 2, 3, 4, 5. 5 over 30, which reduces to 1 6. So again, you can do the organized list, and it still makes sense. Okay? Do the probability that the second is green. You get a half. And so you could do that same thing that we did with those. I hope that makes sense to you. That's it.